All right, so we're back here for part 2. And what we did was we had constructed a perpendicular bisector of segment EF. But then we started choosing points on on the perpendicular bisector. By the way, if I call that L, we can say that line L is perpendicular to segment EF for that. And what we were showing is that when we measured the distance from each of these points to the endpoints of the segment, they were the same every time. Now, I don't mean that they're all the same. These two here are definitely longer than from point A or from this point right here. But from each individual point, the two segments that we can draw there will be the same distance. They'll be congruent to each other. Well, here's why. If I go back to the original AE and AF, notice that we have two triangles here. And in the two triangles, we already know some things. M is the midpoint of EM and FM, which means that we know that EM and FM are congruent. We know that AE and AF, hold on. Let me backtrack here for a second. What we've discovered here, there's a rule. It's called the perpendicular bisector theorem. Okay, perpendicular bisector theorem. A theorem is a rule that we can prove. It's something that we know to be true because we can prove that it's the case. If a point, so here's what it says. If a point is on the perpendicular, and I'm going to abbreviate, is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of that segment. If A is on this perpendicular bisector, it has to be the same distance from AE and AF. This point here, if I gave it a name, if it's on the perpendicular bisector, these must be congruent because they have to be, this has to be the same distance from the endpoints E and F. The reason why perpendicular bisector, we know that these are congruent. That's the bisector part. We know that these are right angles. These are congruent. We also have a common side AM. Now, because this is getting a little bit sloppy here, let me draw out what we have. So here's the triangle A, here's E, here's F. We drew the perpendicular bisector, which created this. And we also know, this is the point M, segment AM is a side in both triangles. So that's congruent to itself. Now looking at this picture here, we can prove, based on this information, the triangles are congruent by what we call side angle side postulate. Triangle AME is congruent to triangle AMF by side angle side. And since the triangles are congruent, that means that all of their corresponding parts have to be congruent. So this segment and this segment, they correspond to each other. So we say therefore, okay, this dot, 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 that means therefore, this triangle of dots. In conclusion, segment AE is congruent to segment AF, and that's by a rule called CP/CDC. The corresponding parts of congruent triangles are congruent. If the triangles are congruent, Well, that means they have the same size and the same shape. Therefore, all of their corresponding parts have to also be congruent. So based on this, I could also say, by CP/CDC, angle E and angle F have to be congruent because they match up to each other and the triangles are congruent. I could say angle EAM is congruent to angle FAM, again, by CP/CDC. So if you have a perpendicular bisector, if you have a point on that, then it will always be equidistant from the endpoints of that. Now, one more thing that we'll mention here for this theorem, not only is this true, but so is the converse. And the converse is if I switch the hypothesis and the conclusion. So if I say, if a point is equidistant, and I'm kind of shorthanding here, from the endpoints of a segment, then it must, I'll say it is on the perpendicular bisector, okay, perpendicular bisector of that segment. Okay, so if a point's on the perpendicular bisector, it's equidistant from the endpoints. If a point is equidistant from the endpoints, then it's on the perpendicular bisector. Okay, so kind of in shorthand here, perpendicular bisector implies equidistant. The converse of this is where I switch my hypothesis conclusion. Equidistant implies it's on the perpendicular bisector. Now that's not always true. The converse is not always true to what we call the conditional, but in this case, it actually works. Okay, so again, there's a lot that we did here, but we just proved that the construction is going to give us this relationship where all these points are always going to be the same distance. Now, just to go through this again, because this construction, you got to practice these. If I want to take GH and draw that perpendicular bisector, first of all, you should pause the video, try to do this yourself. All right, now, hopefully you've done it. Hopefully it worked. But the process, I'm going to anchor on G. Now, I'm going to slide the setting. As long as the hole is more than half, then what we'll get is the intersection points. Okay, so I don't need to make it huge. I don't want to run off the paper for that. So I'm going to arc above and below. Just draw one big arc. And then I'm going to come over to point H, anchor on H, then arc above and below. You'll notice that my compass slid a little bit because this line is a little thicker. Okay, so again, in a perfect world, that would never happen, but it looks pretty good. There's my two intersection points. And then I connect them. Now, again, two things should happen. This intersection point should be the midpoint. These certainly look congruent, and they also look perpendicular. They look like right angles. So I think I've done a good job there. Okay, so that is a perpendicular bisector. Now, the next one we're going to do, we're actually going to skip the back of this, which is other types of perpendiculars. It's kind of the same process though. I want to go to an angle bisector, which is very similar. It's just that now we're going to create two congruent angles. So let's take this angle A here. This is our vertex. Well, we're going to anchor on that point. So we need a point to start from. So let's anchor on A. And we're going to draw an arc through both sides of the angle. So through both of these rays. And the idea is that we're creating 2 points. Let's call those B and C. And by doing it like this, by using the same arc, then AB and AC should be the same. Okay, that's the whole reason for this, is we have to be consistent. So now what we're going to do is anchor on B. And we're going to draw one arc out here in between the sides of the angle, so in the interior. So draw one arc, doesn't need to be huge. And then I'm going to come over to C with the same setting. I'm going to draw the arc again. And notice that they intersect. That's another point. I'm going to call that D. And if we connect that, so if we connect A to D, if we've done this right, and this looks good, I think we did, we should have two congruent angles. So segment AD, or this ray, AD, is an angle bisector. We've bisected angle BAC. So we've created, we'll say angle BAD, that's this one. The top angle should now be congruent to angle CAD. So that is an angle bisector. Okay, so now you can go ahead and try the same thing with angle B here. So again, we're going to anchor on this point on B, and I'm going to draw an arc. To create two more points. And then from those 2 points, now once I create the two new points, it's okay if I want to change the setting. So if I want to make that a little bigger, I can. I'm going to arc one time from each point, but I have to do the same arc. Same setting, same hole. You can see it's sliding a little bit here. And where they meet, my intersection, I connect that to the vertex. And that is an angle bisector. Okay, let's do one more here on this video. Let's do a congruent angle. So now let's copy an angle. So let's take angle A, and whatever that measure is, we want to draw the same angle down here. To start this, I am going to just draw a ray. Now that endpoint, let's call that A prime. Okay, because I'm going to start, here's the vertex for A. I want to copy that, so I'm going to put the vertex here, call that A prime. Now we're going to start this the same way that we did the angle bisector. Let's anchor on A, and I'm going to draw an arc through both sides of the angle, and that's going to create 2 points. Let's call those points B and C. Now whatever we do to this top angle, we need to copy it down here. So I just drew that arc. Well, let me do the same thing here. I'm going to anchor on A prime. Now something kind of interesting that you notice is that you might be saying, wait a minute, we only created one new point down here. We only created the point that corresponds to C. We'll call that C prime. Where do we put B? Where does B prime go? It's somewhere on here, but we don't want to ever guess. You know, you might look at this and say, well, you know, if I put it there, that's probably close. And it might be, but we're not trying to be close, we're trying to be perfect. So we have to figure out exactly where B prime is going to go. Well, let's come back here and let's measure the distance from C to B. And you might say, oh, cool, we have a ruler. Let's go ahead, we can just measure that and then just copy that down here. And again, yes, you can, and you'll be pretty close, but you won't be perfect, and we want to be perfect. So I'm going to measure this with the compass. I'm going to anchor on C. And then I'm going to adjust the setting so that the hole goes right over point B. This is how I'm going to measure. Now to verify that that actually is a good measurement, I'm going to draw a small arc right here. And let's see, does it go through B? It does. So I'm going to take that measurement now, come down to C prime, anchor on C prime, and then draw the arc again. And where they intersect, actually I was pretty close when I guessed, that is B prime. And then the last thing we'll do is connect A prime to B prime. And what we should have here is two congruent angles. And again, if they look congruent, if it looks good, then you're probably good. So I think angle A is congruent to angle A prime. I could use a protractor if I really want to verify this. All right, that is the end of the second video.